Hi all, welcome to the third session of the day. Right now we'll be having the talk on GPU programming in pure Python by Bryce. Welcome Bryce to the stage.
So hi folks, I'm Bryce Adelstein Lelbach. I'm a principal architect at NVIDIA, where I lead our programming language design and evolution. And I also help with designing our libraries and our compilers. So my job is to make every major language a GPU language, from Fortran to C++ to Python to Rust to JavaScript. So I've been involved in the leadership of many programming languages. I chaired the Standard C++ Library Evolution Group and the American Programming Languages Standards Committee. And I'm very excited to be here giving my first talk at PyCon. And I've been programming for about 15 years, and since the start, my focus and passion has been parallelism. And fundamentally, this is a talk about parallel programming. So parallel programming is hard because we think sequentially by default. Parallelism is often seen as challenging and complex, like a tool to be used sparingly and cautiously, and only by experts. But today, we live in a parallel world. Almost every hardware platform is parallel, from the smallest embedded devices to the largest supercomputers. And because of the nature of processor manufacturing and design, we are now increasingly forced to explicitly program that parallelism to get more performance. And so we have to change our mindset. Anyone who writes code must learn to think in parallel, and parallelism must become our default way of thinking. So today we're going to talk about parallel programming specifically on GPUs. So what exactly is a GPU, and what are they good for? So the last speaker mentioned is not going to really get into GPU architecture much. I'm going to get into GPU architecture a bit here today. So modern CPUs and GPUs are both general-purpose processors that can run almost any kind of code. GPUs are not like this exotic thing like they were 10 or 15 years ago. These days, they can run just about anything. Where they differ is in what types of workloads they are optimized for. So CPUs are optimized for latency. They have more powerful cores and threads, but less of them. They have less latency to access memory, and typically more memory to access, but at the cost of lower throughput. Now, GPUs are optimized for bandwidth and for parallelism. So they can run hundreds of thousands of threads, although each one of those threads individually has less processing power than a single CPU thread. Their memory latency is higher, so you have to wait longer to get things from memory, but the memory throughput is much, much greater. You need a sufficient workload to be able to benefit from GPUs. If you're trying to add up like 1,000 integers or sort like 100 floats, you're not going to see a speed up from parallelizing that with a GPU. And in fact, you'll probably see a slowdown because there's a lot of overheads associated with getting the work over there. Now, your workload is defined by how much compute you're doing per element, or your operational intensity, and then how many elements that you have. So a good rule of thumb, I get asked this a lot, a good rule of thumb is that if you're doing like linear amount of compute, if you're doing something that's like applying a function to each element, or you're summing them up, then you need gigabytes of data for that to be able to pay off. If you're doing more than ON compute, if you have a higher operational intensity, for example, if you're sorting or you're doing matrix multiplication, then you can see speed ups with less data than that. So this is a talk about writing speed-of-light GPU kernels in pure Python. And the first law of GPU kernels is to avoid writing GPU kernels. There are many excellent GPU accelerated libraries out there, and most of them have Pythonic interfaces. There's libraries like CuPy and PyTorch and cuDF and cuBLAS and cuFFT and cub. And not only will these libraries make your life easier, they'll often give you better performance because they're written and tuned by a team of experts. So you should try libraries before you start writing your own GPU kernels. For almost every use case that you can imagine, there is an existing library. And so if there is an existing library, then you should try it out and benchmark it, and if it delivers the performance that you need, then just use that and don't reinvent the wheel. But sometimes there's no library that does what you need, or you've tested and found that you can't get the perf you need with the libraries that do exist. And that is when you should consider writing your own GPU kernels. The good news is that now you can write those kernels in Python and get the same performance that you'd get writing native code with CUDA C++. So the primary way to write GPU kernels in Python is with Numba CUDA. So Numba is a JIT compiler framework for Python that's fairly widely used and popular, used a lot for CPU JIT optimizations. So it takes Python bytecode, or AST, and lowers it to Numba IR, which is a compiler intermediate representation, and then it performs type inference and some other transformations upon that IR. And then it lowers the Numba IR to a backend IR, such as LLVM IR, NVVM IR, or MLIR. And Numba supports NumPy arrays and frameworks that build on top of NumPy, like SciPy. So Numba has a compilation mode, the default compilation mode, that's called NodePython, in which it will compile code outside of the standard Python object model. So it'll take your code and it'll compile it with a different set of semantics. And that means that your code can run without the involvement of a Python interpreter or runtime at all. This means that there's no reference counting, and that there's some things that you can't do, like some sort of reflection type things. You can't like dynamically add an attribute to an object, etc. One big implication of this is that the caller of a function that's JITted in this mode is responsible for maintaining the lifetimes of any objects that are passed in particular if it's a function that's being JITted that launches some asynchronous work. It's not going to take any reference counts. So this model has some semantic compromises, but it is best for performance because it makes it very easy to lower Python code to native code. Many Python-based DSLs, such as Triton and Jax Palace, use this same model. Numba is modular, extensible, and hackable, which is a large part of why it has been successful. You can easily customize how Numba lowers things. For example, if you wanted a function in your code to be lowered to a certain assembly instruction, you could write a Numba extension for that. If you wanted one of your classes to have a certain layout in memory when JITted, you could write a Numba extension for that. So what exactly is a GPU kernel? So a kernel function is a function that's run by many threads at the same time. So we're going to write our first one, which is just going to copy elements between two arrays. So we must decorate our function with cuda.jit to use it as a kernel. The inputs to our copy kernel will be two NumPy compatible arrays. You can pass NumPy style arrays into kernels and access their elements, but you can't call array methods on them in device code. And that's something that you'd want to avoid doing anyways, because the array method would be executed by a single GPU thread. And as we discussed, each GPU thread is a lot slower than a CPU thread. So there's a lot more of them, but what you really want to do is parallelize array operations across threads, not have a single thread doing something like summing up an array. So the first thing we do within the body of our kernel is determine the unique index of our current thread. So cuda.grid gives us a global thread index. These thread indices start at 0, and each thread that's executing the kernel will get a different thread index. And we can use this to pick which elements of the input we're going to work on. So then we copy one element from the source to the destination using that unique thread index to select the element that we're going to copy. So if we have 8 threads, for example, we would copy 8 elements like so. Now on GPUs, threads are grouped together into a hierarchy. The lowest level of that hierarchy is a warp of threads. So all of the threads in a warp execute the same instruction together at the same time. Some of the threads may be inactive during the execution of a particular instruction, but they aren't doing something else. They're still executing with the warp. Warps have a fixed size that's dictated by the hardware architecture. It's been 32 threads essentially for all of history on NVIDIA hardware. Threads in a warp can communicate with a variety of different fast synchronization primitives. Now, warps are grouped together into thread blocks. All of the warps in a block run at the same time, but each warp may be executing different code. Blocks can synchronize with each other and communicate via a special kind of fast memory called shared memory, which we're going to discuss a little bit later. And we call the set of blocks that are executing a kernel a thread grid. Blocks and grids can be 1, 2, or 3-dimensional. Now, we don't call our kernel function as we would any other Python function. Instead, we have to launch it, explicitly instructing CUDA how many threads to use and in what configuration. So kernels are launched from the CPU, but they run on the GPU. They're the entry points for GPU code. If you're using GPU-accelerated libraries, which is what you should be doing instead of writing kernels, you don't have to worry about launching the GPU kernels, then the library will do it for you. But today, we've got to do it ourselves. To launch our kernel, we need to provide both execution parameters and the function parameters, the parameters to the kernel itself. So the execution parameters are provided via the index operator in numba, and the function parameters are provided via the call operator. So the first execution parameter is the number of blocks, which is 2 in this example that we've got shown on the screen. And the second execution parameter is the number of threads in each block, which is 4 here. So now let's look at how we can write a slightly more capable copy kernel. So our previous copy kernel copied 1 item per thread. Now that's not great for performance or functionality. We won't saturate memory bandwidth with so few operations per thread. We also don't want the number of threads to be dictated by the input size. So we'll write a version that copies multiple items per thread. The quantity is specified with an additional parameter. When determining our unique thread index, we need to multiply it with the number of items to account for the extra items that all other threads before us will have handled. And we'll have a simple for loop that will copy all of our items, the items that this thread is responsible for. And when we launch our kernel, we need to calculate how many blocks to launch. And that will be the number of items in the array, n, divided by the number of thread blocks, b, times the number of items per thread, t. The second parameter is just our thread block size, b. Now let's think about how this kernel will access memory. Here's a table showing what a grid of 4 threads will access when running this kernel. So thread 0 will access items at index 0, then index 1, then index 2, etc. Now, this looks great, right? Because we're moving through memory contiguously without any strides. And so with an optimizing compiler or a JIT that can reorder the loads and stores and group them together, they could then be combined into vectorized operations. And even if this code isn't vectorized or JITted, it would still have good memory locality. It's accessing things that live near each other. So we should have good prefetching and good cache performance. And all of that is true on CPUs, but not on GPUs. Remember, on GPUs, all the threads in a warp are executing instructions together. So on the first step, the warp will load from index 0, 4, 8, and 12, 1 load for each one of the threads. And that is not a contiguous load. That is a strided load. So we're going to have to issue from the warp 4 separate loads that will have to go through the memory hierarchy. So we have to flip our thinking here. Let's try this again. And this time, we're going to have each thread do strided loads and stores, such that the entire warp will load from a contiguous block of memory at each step. So we can no longer rely on the cuda.grid utility that provides a global linearization of the thread hierarchy. Now we'll have to access the raw components of our thread's coordinates and the block dimensions to calculate the right stride. So block dim is the shape of our thread block. We're just working in one dimension for now, so blockdim.x is the number of threads in the entire thread block. Block index is the index of our thread block in the thread grid. And thread index is the local index of our thread within the thread block, unlike the global index that we got from cuda.grid earlier. And so next, we need to determine how many items are handled by each thread block, which is just threads per block times items per thread. And we're going to call this value tile. Now we figure out the start of the chunk of items that this thread is responsible for. And this will be the thread's index in its block, plus the number of items that all lower thread blocks will handle. Then we do a strided loop copying elements, where our stride is the number of threads in our block. So now let's take a look at the memory access patterns here. Now, each thread in each warp will load from a contiguous set of indices, 0, 1, 2, 3, in our example with 4 threads. And the warp will issue just one load here, which is far more efficient. This is called memory coalescing, and it's a very important part of getting peak performance on GPUs. The GPU compiler can reorder the loads and stores, and then it can combine them up to the size of loads and stores that it supports. While different warps within a thread group issue instructions independently of each other, there are also benefits to this memory pattern at the thread block level, such as improved cache behavior and ultimately less traffic to global memory. So in our first naive example, we had what is called a blocked arrangement of the aggregate tile of items that each thread block handles. So each thread was responsible for a contiguous set of items in the global input and output. But then in our second example, we switched to a striped arrangement, which is often more efficient, where the aggregate tile is partitioned across the thread block with a stride of the thread block size. So there's 3 types of memory that GPU threads can utilize, and it's important to understand them before we move on. So local memory or register memory is the memory that is private to each thread. So this is what's often called stack memory on CPUs. This memory is used both implicitly for local variables, but in CUDA-Python it can also be explicitly allocated. It is incredibly fast to access as it is physically located within the GPU processor core. Now, shared memory is storage that can be accessed by all the threads within a block, and it must be explicitly allocated. Shared memory is used to implement block-wide communication protocols. Now, like local memory, it is very fast to access, not quite as fast though. Shared memory has the same performance as the L2 cache, and it actually sits right next to the L2 cache in hardware, and it uses similar technology. It's implemented with similar underlying technology as the L2 cache. Then finally, we have global memory, which is, if you're not familiar with GPU programming, global memory is just what you're used to thinking of as memory. And so this is what's also known as the heap. Global memory has hardware caching. There's an L1 cache, an L2 cache, etc., unlike local and shared memory. And that's good because accessing global memory is very, very slow, not just for GPUs, but for CPUs as well. However, CPUs are out-of-order processors with lower per-thread latencies, so they experience less of the slowness than GPUs do. GPUs are, for the most part, in-order processors, so we have to suffer and experience the full latency of memory loads and stores unless we can hide it by subscribing the hardware. So we either hide the latency by batching operations, or we avoid it by minimizing the amount of global memory traffic. So now let's take our copy example one step further. Instead of writing all the low-level I/O and indexing ourselves, we can use a library. cub is a CUDA C++ library of kernel authoring tools. It has a number of cooperative parallel algorithm primitives, such as loads, stores, reductions, scans, and sorts. So a cooperative operation is called by multiple threads at the same time. A cooperative operation does not create or launch any new threads. Instead, existing threads must explicitly participate in the cooperative by calling the function. There are versions of these cub facilities for all the levels of the thread hierarchy, from within a single thread to a warp of threads to a thread block, and even across the entire grid. And cub has been the gold standard and speed-of-light solution for GPU kernel authors for many years. And it's widely used to implement many of the frameworks that we all use. And now you can use cub when writing CUDA kernels in Python. So cub's primitives are available in the cuda.cooperative module that we've recently released in beta. And the best part is that with Numba CUDA and cuda.cooperative, you get the same performance that you'd get if you write your kernels in native CUDA C++. So let's use cub in our final version of the copy kernel. So first, we're going to set up our imports. We need NumPy, Numba CUDA, and the cuda.cooperative module. N will be the size of the input and the output. And then B will be the number of threads in each block. And T will be the number of items that each thread will load into local registers and then store out to global memory in one batch. To use CUDA cooperative algorithms, you need to instantiate an algorithm object outside of your kernel. And this is necessary today because we have to JIT compile the underlying CUDA C++ code before the kernel invocation, and we need to know about it before we start executing the kernel. So the block-wide load and store algorithms take 4 different parameters: the data type, the number of threads per block, the number of items that each thread works with at one time, and which block-wide I/O algorithm to use. So there's 6 of them. We're only going to talk about 2 or 3 today. So the direct algorithm loads data in a blocked arrangement that we discussed earlier. The striped algorithm loads data in the striped arrangement that we used earlier that gave us memory coalescing. There's also a series of transpose algorithms, which will load data in a striped arrangement, but then they'll locally exchange the data with other threads in the block so that you end up with the appearance of a blocked arrangement, so that each thread is actually dealing with a contiguous region of elements, even though they were loaded in the efficient striped manner. So for right now, for this copy kernel, we're just going to use striped. CUDA cooperative algorithms utilize that fast block-wide shared memory that we just discussed. And so we need to calculate how much shared memory will be used by our algorithms. We also need to collect the set of binary objects that we'll need our kernel to link against. And so I'm just going to define this glue configs utility function that can help us do this. So we must pass the deps list as the link parameter to the cuda.jit decorator. And we're hopeful that this linking will be done automatically in the future, but today you have to explicitly do this if you want to use CUDA cooperative. Within the kernel, we need to allocate the shared memory for the algorithms, which we do with the cuda.shared.array function that returns us a NumPy-like array. We do now have a version of the algorithms where they will implicitly allocate the shared memory themselves. That has the disadvantage that if you're using 2 or 3 algorithms within a kernel, each one will allocate separate shared memory, and they won't be able to reuse that shared memory, which is less efficient. But in some cases, it's perfectly fine to use the implicit mode. So next, we need to allocate some local memory, some registers, to store the batch of items that will load. And then we calculate the base index of the items that we're responsible for, just as we did in the prior example. And now we can do our block-wide load. So we pass it the temporary storage, the chunk of global memory that we'll be loading from, and the local memory that we'll be loading to. And both of those parameters are just NumPy-style arrays. And then we do our global store, passing it the temporary storage, the chunk of global memory that we're going to write into, and our local items. Now, in between these two block-wide operations, we need to synchronize all the threads in the block because the shared memory will be used by both the load and the store, and they'll reuse each other's shared memory, and we want to avoid a data race. And so we can use sync threads for this. Sync threads is a synchronization primitive that synchronizes all the threads within the block and ensures memory ordering between them. So it's a cooperative. That means that all the threads that are participating in the synchronization must call it. And finally, we set up our inputs, outputs, and launch our kernel just as we did before. And that's it for this example. We've got an efficient and scalable copy kernel written in pure Python. And this will be JIT compiled to the same thing that you'd get if you wrote the equivalent CUDA C++ code. So now let's move on to a more advanced example, matrix transposition. So transposing a matrix flips it on its diagonal, switching the row and column indices of all the elements. So for example, the value at 3, 1 here is exchanged with the value at 1, 3. So using a row major layout, also known as C-style in NumPy, our matrix will have this representation in memory. All of the elements in a row will be stored contiguously in memory. Now let's look at the code. First, the problem and grid configuration. So our input and output will have a 2D shape. This example that we're writing will support rectangular matrices as well. So the best strategy for an efficient transpose on a GPU is to split the input into 2D chunks, each of which will be handled by a different thread block. So tile will be the dimensions of our square chunks of the input. Next, we determine the size of our thread grid by calculating how many thread blocks we'll need to handle all the tiles. We'll come back to the kernel in a minute, but let's look at how we launch it first. So first, we create our input and output, and we'll pass them as flattened arrays into the kernel so that we can do some indexing tricks. In our prior examples, we just used NumPy arrays and passed them directly to our kernel, and that works fine, but under the hood, it will copy the inputs to the GPU before the kernel launch, and then it will copy them back afterwards. Now, that will force the kernel launch to be synchronized and will implicitly perform an expensive operation, that data transfer there. So often it's going to be better to manage this explicitly. So NumBaCuda has a special device array type for this purpose and a facility for converting NumPy compatible arrays to device arrays and transferring them between host and device, which we're using here. But you can also use a library like CuPy or PyTorch to create and manage device arrays. And NumBaCuda works with them as well. And that's actually what we generally recommend people do, is to just use CuPy to create and manage your device arrays. So now let's move on to the kernel itself. So first, we must set up the cooperative primitives that we're going to use. So we need a block-wide load and store, just like before. And remember, the parameters for these are a data type, the number of threads per block, the number of locals per thread, and the algorithm. So our chunks of data are tile times tile large. So we're going to have tile threads in each block and tile locals per thread, giving us the desired size per thread block. And we'll use the striped algorithm just as we did before. We need an additional primitive here, a block-wide exchange that we'll use to do the local transpose of each tile. And then finally, we determine the temporary storage requirements and get the binary objects that we need to pass into the kernel decorator. And now let's look at the kernel itself. So first, we allocate shared memory for communication and tile elements of local memory. And then we manually calculate the base of the tile in the global input using row major layout. And note that we use both block index and block index X and block index Y here because we have a 2D grid of thread blocks. And then we do our striped and strided load from the global input into our local memory. And our stride through memory will be the number of rows. And then finally, we do async threads after the load so we can reuse shared memory in the next operation. So let's look at what we're actually doing here. So for each block, our strided load gathers tile number of partial rows from the input. And this strided memory access pattern, it's a little bit of suboptimal. So why not just load entire rows, which would be contiguous? Well, we want to maximize memory reuse and caching by performing local transposes of the tiles in each thread block. And then to do that, we need chunks of items that are logically next to each other, that are logically matrices. And so now that we've loaded the items, we need to do the local transpose, which is going to look like this. And so now let's look at where we do this in the code. We're going to use this striped to blocked exchange to do this. And this will take block-wide data in a striped arrangement and transform it to a blocked arrangement, which will affect the local transpose that we're after. And so next, we need to write the locally transposed items to the output. So the whole chunk itself needs to be written back to a transposed chunk in the output, as shown here. So there's two levels to the transpose. First, we transpose locally, and then we have to transpose the entire tile into the right place in the output. So in the case of block 1, 0, we need to write to the indices that block 0, 1 would read from. So that will give us this. And then at the same time, block 0, 1 will be writing to the indices in the output that block 1, 0 read from. And that will ultimately give us this. So to transpose the store to the output, we need to switch from row major indexing to column major indexing, which we do here. And then finally, we do our strided store, this time with a stride of the number of columns. And then with that, we are done. We've got a speed of light matrix transpose CUDA kernel written in pure Python and small enough to fit on a slide. So this will perform as well as the CUDA C++ equivalent would. So now let's move on to one more example, which is a softmax kernel. So the normalized exponential function, softmax, takes a vector of numbers and normalizes them to a probability distribution. So to put it more simply, it takes a 1D array of numbers and it converts each of them to a value between 0 and 1 such that all of the values add up to 1. So this is commonly used in machine learning, for example, as one of the final layers in a classifier, or in reinforcement learning for action selection. It's a key element of the popular flash attention algorithm. And so today we'll look at how to compute the softmax of many vectors at once in parallel. So to compute the softmax, you take the natural exponential of each element of the input, and then you divide by the sum of the natural exponentials of all the elements of the input. So for numerical stability, we derive a slightly different formulation to avoid summing numbers of drastically different orders of magnitude. So we subtract the maximum value in the input from each value before taking its exponent, and then we divide by the sum of those differences. And the maximum value will cancel out in the division, since the exponent of a minus b is equal to the exponent of a divided by the exponent of b. Sorry, I know that's a lot of math. I'm a math major. So this is the formula that we need to work with. So we must perform two operations here that require communications between threads, and that is determining the max and summing the exponents. So both of these are reductions. Parallelizing most algorithms boils down to a combination of reductions, scans, and element-wise function application. So we're going to partition our input into rows, each of which will be handled entirely by a single thread block. So let's start with our problem and grid setup. So we'll have a 2D input and output, and we'll parameterize how many items each thread has in local memory, which will allow us to control register usage and batching. The number of threads in each block will be dictated by the input shape and the number of items in each thread. So a more advanced version of this kernel and the transpose kernel would use additional iteration within the kernel to allow us to set the amount of locals per thread and threads per block while also supporting arbitrary input size. But that's a little bit more complicated, so we're not going to get into that today. So next, we're going to create our cooperative primitives. This time we're going to have 4 of them. So once again, we need a block-wide load and store. But this time we're using a different I/O algorithm, warp transpose, which loads striped data and then transposes locally to blocked. And we're using this to ensure that within each thread, sums are performed in the original order of the input, which helps to improve numerical stability. So next, we need a max reduction. And we'll create one by instantiating all reduce with np.fmax as the reduction operator. So then this is going to go through each row and find the maximum element. And we also need a sum reduction. And we'll pass np.add as the operator for this one. So now let's move on to the launch. So this time, we're going to pass 2D arrays into the kernel, which we create here. But the grid shape will be 1D, one thread block for every row. So now let's take a look at the kernel itself. We allocate shared and local memory just as we did in prior examples. And then we load the entire row into local memory. And as we just discussed, this will be a striped load that will then be transposed to blocked locally. And then next, we find the maximum in each row. And then we compute the exponent of each item minus the maximum. And then we sum up all of those exponents. And we divide each of the items by that sum. And then finally, we store that entire row to the output. And that's it. We are done. We've got an efficient softmax kernel implemented purely in Python. So let's talk about some of the takeaways from today. So first of all, don't do any of this. Use libraries whenever you can. Avoid writing your own kernels from scratch. It should really be a tool of last resort. And what I've shown you here is a very simplified view of the world. In the past 5 years, writing CUDA kernels has gotten more and more complex as we've had to expose more and more features and accelerators up to users for people to be able to get perf. And so these days, even writing something like a simple copy kernel is not as trivial as I showed if you really want to get the absolute speed of light. But if you do want to write your own kernels, you can do it natively in Python, and you can get the same performance that you'd get from CUDA C++, and you can access all of our device-side libraries. And if you're writing a kernel where you're just calling a bunch of our device-side libraries, that's perfectly fine. You're not really writing a kernel yourself, you're just sort of composing it together. You're letting somebody else do the heavy lifty of figuring out how to do an efficient load, an efficient store, an efficient FFT, an efficient matrix multiplication. And then finally, you've got to think carefully about memory layouts and access patterns when authoring kernels, because the way that GPUs want to access memory is very different than how CPUs want to access memories. So I got a couple things I'll plug. If you want to learn more about GPU programming, there are many talks available to watch on demand from GTC 2025, NVIDIA's developer conference. We've also released a new open source CUDA curriculum with tutorials, notebooks, and other learning materials in both C++ and Python. You can find this on our Accelerated Computing Hub on GitHub. Don't worry, all the QR codes are going to be on one slide later. And then if you're interested in parallel programming, algorithm design, and programming language development, my buddy Connor and I have a podcast, ADSP, Algorithms plus Data Structures equals Programs, available on all streaming platforms. Go subscribe now. And then finally, we have NVIDIA's DLI platform. And if you go to the QR code on the DLI platform and sign up, you will get free access to one of our high-quality CUDA courses to learn all about GPU programming. And then final thing, we've got 2 open spaces today to talk more about GPU programming. One will be immediately after this talk, and we have a sprint planned for later in the conference. So thank you all for your attention. I think we maybe have time for 1 or 2 questions. I'll have to check with my person here. I think we do. And hopefully I'll see you all at next year's conference.
Thank you so much for this wonderful and informative session. We have around 5 minutes for questions. Please use the mic at the back for asking the questions. Thank you.
Total newbie question.
Yeah.
Why, is it like a technical or is it a legal reason that, like, CUDA seems cool, why can't this be ported to other GPU architectures?
I can't really answer that question. I mean, it's like, CUDA is very specific to how NVIDIA's hardware works. Not everybody else's hardware works that way. And we are not in the business of writing software for other people's hardware. And also, we wouldn't be the best people to do it. So that's really what it comes down to. There are a lot of solutions, especially in the Python space, that let you write portable code. CuPy, for example, has an AMD backend as well. Things like PyTorch have backends for a bunch of different platforms. Things like JAX have backends for a bunch of different platforms. But CUDA is like it's the software for our platform, and that's just always going to be fundamentally what it is.
Thanks.
Quick question. So you mentioned that not to do these algorithms yourself, to kind of leave it to the experts. Have you seen that like really high-end experts really improving the performance over kind of like the stock kind of algorithms that you have?
Yeah, I mean, people, like, there is a small handful of people who can write, like, the speed-of-light kernels. We tend to hire a lot of those people, but, like, there is a very small number of people who can do that. But the other part of it is that you might be able to write the speed-of-light kernel for the GPU today, but you're not going to be able to write the speed-of-light kernel for the GPU that's going to be released next year or the year after that, because you don't know what that architecture looks like. The people who do are, like, the people who work at the hardware vendor, they do, and they'll write the libraries so that on day one, you have speed-of-light performance on the latest and greatest hardware. Whereas if you're doing it yourself, I mean, you can, but you're not necessarily going to you know, have the same lead time that we would.
Okay, thank you.
Thanks, it was a great talk. I guess I'm curious to hear your thoughts on you know, the Triton programming model, essentially allowing the user to think at the block level and abstract away some of these details, I've found it to make me incredibly productive. So what do you think the future looks like in terms of like, is that model sustainable, or are there going to be issues where essentially maintenance of the compiler stack sort of outweighs the productivity it affords?
I got one slide that should answer your question on that,
Fantastic.
which is cuTile, which is a tile programming model for GPUs that's aimed to simplify GPU programming with a higher level array-based programming model that automates block level parallelism and memory movement, delivering portability especially for tensor cores. And this is built on top of TileIR, which is this novel new MLIR low-level compiler stack and intermediate representation for tile programs that we've developed. We announced this at GTC this year. It will all be released sometime soon. I'll be giving a talk at SciPy that will be the first public talk where we're going to really go more into details about how cuTile and TileIR works. There are a couple sessions at GTC that talk about cuTile and TileIR, and also the lower level cutless and Qt dialects. So Stephen Jones's CUDA New Features and Beyond talk, and Leo Fang's talk on 1001 Ways to Write a GPU Kernel in Python. And then the series of talks from the Cutlass folks, if you're looking for more information that's immediately available now. But there will be more details available at SciPy. Encourage everybody to come to SciPy. We can chat more about it there. Find me afterwards if you want to ask more questions about that.
I was curious, like I really enjoyed the talk, but some of the kernels looked unPythonic.
Yes.
But like a lot of the cub primitives seem to map to things that are in Python, like a reduce. Is there any attempts to like reduce CUDA aware?
I think we'll get there. I don't think it's going to look exactly like that, but on device side, it's a little tricky because of the need to deal with like linking and to deal with like the discovery of the algorithms. We're working on a model where you won't have to pre-declare the algorithms. I actually think that that might be pushed now to the repo where you can just use the primitives directly in device code. So that alone is just like a lot cleaner. And if you're willing to use more shared memory, not having to deal with the shared memory allocation just like eliminates a whole big piece of it. The next step of that, I guess if you're looking for something that's more like Pythonic, like what you want is cuTile. Like this is, hang on, let me see if I can find the other slide here. Like this is like on the right is what the speed of light cuTile softmax implementation looks like. On the left is what the speed of like what the code you'd write in NumPy. I mean, you could write a simpler version of the code in NumPy, but if you want something that's really high level in Pythonic, like this is your thing. The CUDA SMPTE programming model is still something you'll need to reach for if you need to communicate between threads, because you can't do that in the tile model. But this is probably the answer that you want.